Okay, this is uniformly accelerated motion. Your work number is I think it's 1345. I hope I did it right. I closed my computer. It'll be on the site if not, it'll be on the assignment. Okay, so I'm going to do 3-2 and 3-3 together here. Before, what we looked at was this equation. The acceleration, average acceleration, is change in velocity over change in time. Final velocity, initial velocity. The little knot or O symbol means initial velocity, final velocity, average acceleration. TF is T final, TO is initial time. Final initial. Well, in all the problems we're going to be working now, we're going to talk about what's called uniform accelerated motion. What that means is motion is going to be going constantly accelerating or constantly decelerating. There are many cases in real life, practical cases in real life where this happens. The best example is you're driving in a car along the road or on the freeway. How about on the freeway? You're driving on the freeway, 50, 60 miles per hour, cars going, maybe the carpool lane, your family or whatever it is, and suddenly you see in front, like maybe like, I don't know, half a mile ahead, you see all the cars are stopped. And you're, oh boy. Well, what do? So you hit the brake. Just like, start the brake. Now, hopefully, if you're far enough away, you don't have to do it suddenly. But you push the brake down gently. You slowly, slow down. Okay, what you're doing is when you push the brake, you're constantly going to be decelerating slower and slower all the way till you stop. During that constant time, there are a lot of things that are true. And one thing is, well, there's a lot of applications I'm going to show you about that. Several equations called the Kinematics Equations. We could call this lesson Kinematics Part 1, and then Part 2 will be the next lesson. All right. There are 5 kinematics equations. This is the first equation, and probably the one that I always will look at the beginning. If we assume that your time is always going to be, your initial time is always 0. So if we do that, then this down here is not the change in time, it just becomes the elapsed time, just the time on your final time. So you start the stopwatch, just say you hit the brake now, the time is going 1, 2, 3, 4, 5, all right, 5.5 seconds, let's just say. So your time was 5.5 seconds. What was your final velocity? Well, if you stopped, it will be 0. And what was your initial velocity? And then your acceleration. All of those would relate according to this equation. Now, we'll use your constant acceleration. If you have a constant acceleration, we don't need to have average acceleration. It'll just be your instantaneous. At every moment, it was always the same thing. So that is the equation that we use for this first lesson. All right. So, actually, what I just told you is there it is written out kind of in better language. Number 1, we'll assume initial time should be time is 0 in our investigations. All right. Number 2, we assume the object moves in a state of constant acceleration. It's constantly increasing or decreasing. Okay. It can also be constantly changing direction, but I will talk about that in a later chapter, like next semester at the end of the year. How about that? So you don't have to worry about that right now. Oh no, that's not right. Next semester at the beginning of the semester. Okay, sorry. Well, I better not even say that because I don't know where we're going to end up with this Zoom stuff. But sometime next semester. Okay. If the velocity of an object is constant, average velocity is equal to your initial and your final for that matter. And so acceleration is constant. Oh, well, actually, it also tells you this. Average velocity is your initial velocity plus your final divided by 2. That's another equation that is always true. Your average velocity will equal both the initial and the final in this case, though. Is that right? No. That's not what I just said was not true. That is true, but what's written on the paper is weird. Yeah, that's not really true. If the velocity is constant. Oh, no. If the velocity is constant, yeah, that's true. But we're not going to be we're not going to be having constant velocity in these problems. I don't know why I wrote that in the notes. That's true, but it doesn't apply. This is what I probably need to be pointing out. This is another equation you can use. If you know initial and final velocity, you can find the average. Or if you know the average in that, you can find the other. Okay. All right, so here's the first equation. First problem. In a time of 2.17 seconds, a runner accelerates from rest to 7.96 meters per second. That means from 0 to 7.96. Calculate the acceleration and assume constant acceleration. Okay, so we know the time. We know it went from rest to 7.96. So look, well, I'm going to write them down. Time is 2.17 seconds. That is the time. Rest, that means 0, and that's your initial velocity. So when something comes to a stop, we say it's at rest. Or if it's at rest and it speeds up, that means it's 0 initial velocity. So rest, it means 0. If you start at rest, you start at 0. If you stop, then that means you end at 0. And your final velocity, it says, is 7.96. That's your final velocity. Yeah, and they want you to find the acceleration. So, for now, we're just looking at these two equations, and that's going to be the one we use, okay? A is V final minus V initial divided by time. Acceleration is, final is 7.96 meter per second, minus the initial was 0 meters per second, and your time is 2.17 seconds. So, 7.96 just divided by 2.17, it's 3.67. Now, it's meters, I'm sorry that I put a 2 there. It's meter per, it will be down here. Meter per second minus meter per second is meter per second over second, so it's meter per second squared. And it's a positive number. You know acceleration is positive because you went from 0 initially up to 7.96. So it's a positive. If you had been slowing down, then it would be a negative. So 3.67 is that first one. Now, it says B, a car traveling downhill. Downhill reached a velocity of 80.70 meter per second in a time of 6.17 seconds. Sorry. If the car accelerated at a constant rate of 4.12 meter per second squared, what was the initial velocity of the car? Okay, so for B, look at all the numbers they gave me. 80.7. Sometimes you might want to write down every number. They also gave you 6.17 seconds. They also gave you 4.12 meter per second squared. Now, when you see meter per second squared, that's a dead giveaway of what that is. And then it says, what was the initial velocity? Okay, so 80.7, it reached that velocity. And even in the end, it says, what was the initial? So that tells us we don't know the initial velocity, but we know this must be your final velocity. This has to be the acceleration because it's s squared. That gives it away. So, and we know that's time. So, they want you to find the initial. So, again, we go to this equation. This is always the first one you should go to in any set of equations. It's to see if it's possible. So, V final minus V initial divided by the time. So, 4.12 meter per second squared equals, your final velocity is 80.7 minus your initial, we don't know, I'm just going to put VO, over the time, 6.17 seconds. Now, what I'll do is, first I'll cross multiply. Well, not really cross multiply, but I'm going to multiply each side by 6.17. Okay? Because that way I'll get rid of that. And this 6.17. Now, 6.17 times 4.12 gives me 25.4 equals 80.7 times, that's it, minus, no, 80.7 minus the initial. Okay, now what I'll do is, it's weird that I have my negative v on this side, but what I can do, well, it's okay. I'll move it to that side. Subtract both sides by negative 80.7 minus 80.7. And that's going to be a negative number, 25 minus 80.7. So it's negative 55.7 equals negative the initial. So since they're both negative, then you could just say, well, you know, divide or multiply by negative 1 if you want each side to get 55. So the initial, I'm sorry, is 55.7. It was 55.7 meter per second. So you started, and does it make sense? You started at 55 initially. You went up, you went up to 80.7. That's why you have positive acceleration, and we got your time in there as well. So it takes some practice going through the algebra of all of these problems. Now, I think that's going to be all that I'll work on this section. I don't think I need to do many more examples, but it's the same thing when you're using this equation. So first you go to this equation, and then this is kinematics. This is part 1. You'll see the worksheet tells you part 1. And part 2, we're going to add, I didn't use this equation right now, but let me just show you how you would use that if you did. Like for example, the problem I just did, let's just say you want to know what was the average velocity during that time. So as the car was speeding up, remember average is an average of all of what you were doing. It is going to be your beginning or the end, but you take, as it says here, your average velocity is your initial plus your final divided by 2. So if your initial was 55.7 meter per second, and if your final velocity is, let's see, what was it again? Oh, 80.7. Then I just divide that by 2. And it says your average during that period, 55.7 plus 80.7 divided by 2 is 68.2. Now, the reason I tell you that is that there'll be problems coming in the future where you might need to find it. It might be useful. Actually, there's one on this worksheet. I know it's the last one. On the homework for today, the very last one, you have to use that equation to solve it. So if you wanted to, as a bonus, you could try that on the last problem on the worksheet here. But otherwise, we're going to add to these 2 equations, we're going to add 3 more in the next lesson. So I'll see you guys.